All right, so now let's pull the internal and external torques together into a concept called static equilibrium. And so this is how we can analyze any exercise that we do. You take a snapshot, so you stop the motion and analyze the external force due to the external load times the external moment arm, and that needs to be equal to the internal or muscle force times the internal moment arm. So the internal torque, muscle force times IMA, external torque, external force times EMA, and those are equal. So the muscle force times IMA is equal to external force times EMA. All right, so let's look at an example of external torque with no weight lifted. It's just the arm weight. And so you go from neutral posture up to abduction. And if I asked you which posture would you want to stand in, you would of course say with my arm down next to my side, or in neutral, anatomical neutral posture. And if I said why, and you said it feels lighter, that would be somewhat incorrect. I mean, it does feel lighter, but the arm weight is the same. Your arm does not lose weight when it's down by your side, but what changes is the torque, the external torque that your arm weight is creating. So when you're in full abduction, you have a longer moment arm from the center of mass to the joint center. When you're midway, that moment arm is even less. And then when your arm is down by your side, it has the, basically in this example, 0 moment arm. So which has the greatest external torque? 1, 2, or 3? Now note that the external force is the same. The pink ball that you are lifting does not change weight as you go through the motion. But this middle section, number 2, has the greatest torque, external torque, because it has the greatest external moment arm. Whoop. And this one is which has the greatest external moment arm. And that is also 2. Which posture has 0 external torque? And that would be position A. I was going to say C, but A. So when the moment arm is 0, the weight of the arm is 35 newtons, so there's 35 times 0 is 0. Which posture has the greatest force? And that would be number 4, because the force, the greatest external force, doesn't exist because the arm is the same weight in all 3 postures. All right, so let's go through some examples. So here we're doing a sit-up, which I probably wouldn't advise, but say we're doing a crunch, so not a lot of movement of the lumbar spine. Is body weight the same between the down phase and say the crunched or curl phase? And that is yes. Your body weight, when you do body weight exercises, your body weight does not change. Is the external moment arm the same from this position 1 to position 2? And that is, it is not the same, right? You have a greater external moment arm in this dotted position 1 than when you pull your upper body closer to the center of rotation, which decreases the external moment arm. What happens if the person puts a weight on their chest? Well, that increases the external force. That's pretty much a no-brainer. But what if you didn't have a weight and you wanted to make this exercise more difficult for someone? Then the only thing you have to manipulate is your external moment arm. And you can change that by putting their hands or arms above the top of their head and extending the external moment arm, which will make the external torque greater. All right, let's look at lever systems. I'm not thrilled with calling it first class, second class. You should just understand resistance and effort, or how they play out. So let's go through these. So for the first class lever, force and resistance are on opposite sides of the center of rotation. So this is your classic teeter-totter. So you have a force on one side times a moment arm, perpendicular distance from the center of rotation to the force, times the resistance times the moment arm. And in this case, since the moment arms are not the same, the forces will not be the same. And you can play around, and this also shows, that the torques are equal. Force 1 times moment arm 1 is equal to resistance force times moment arm x2. And you can think about this if you imagine teeter-tottering with a small child, right? If you didn't want to slam them to the ground all the time, you would move closer to the center of rotation, decreasing your moment arm, and you would push them further back so you could maybe reach a balance point. The second class lever is when the resistance is closer to the axis than the force is. So this is your load that you're resisting, and this is the force you're applying. And this is basically a wheelbarrow or a nutcracker, right? So a wheelbarrow, the handles are out here. You have all this heavy load right here, but it has a short moment arm because here's your center of rotation. You, on the other hand, have a mechanical advantage because you have this nice long moment arm, which is a perpendicular distance away from the center of rotation, and so you apply less force. A third class lever, which is basically what our body is made up of, is that you have this joint center of rotation, you have the force, which in our case are the muscles, very close to the center of rotation, and then you have the resistance, whatever it is that we lift, at the end of our limbs. So what we kick, what we lift, actually has the mechanical advantage. So this is basically telling us that our muscles work incredibly hard, even to lift the smallest item. And here are some examples. The closest thing to a first-class system in the body is using your axis or your atlas, as a pivot point. So you have the resistance of your head and the muscle force pulling you into extension. So kind of nodding yes or no. A second-class system is assuming the fulcrum is about your toes. So you're doing heel raises. The resistance is your body weight, and then the muscle force or the force is your gastrocsoleus complex that's acting further away. So you're acting like a wheelbarrow a bit. And then we have the third class, which is your muscle or your force production is closer to your fulcrum or center of rotation than the resistance is. And here's a summary. First and second class levers, you have an increased force, you have a longer moment arm, so you have a force advantage, but there's less speed and less range of motion. A third class lever system, it's not for force production, right? Because your muscles have to generate tons of force because there's a longer resistance arm, but you have an increased speed and increased range of motion, right? So we have much greater range of motion with our biceps brachii attached onto the radius where it is, as opposed to it being attached mid-radius.